Should probably start recording for you. So we have our mordant, which is aluminum. That's our paper clip. Yeah, and when you initially build these stock solutions to be put together, the hematoxylins to be put together, yeah, you need to ripen it. Okay, so you're going to take it from that light red into that deep purple wine color. Yeah, and that is usually done over a period of 3 to 6 months. Yeah, and it's done simply by setting that bottle in the window of the lab and letting it naturally ripen. Delafields is usually done regressive only, because progressively with Delafields, because it has that extra alcohol in it, going progressively is much more difficult because that alcohol evaporates out. So it's harder to pinpoint it when you're going progressively. So therefore, we use it mostly regressively. Then we have Mayors. Yeah, Mayors, its mordant is also an aluminum. Its oxidizer is sodium iodate. Yeah, the difference between the Harris hematoxylin and the Mayors hematoxylin is it's just simply a little bit different in terms of the recipe, the amount of things that are going into it in that initial makeup of the solution. It does provide a little different shade than Harris. Harris is that purple color that you're used to seeing. Mayors is more of a bluey color. Yeah, now there's a huge debate, there's lots of debates in histology. There's a huge debate on how long, yeah, Mayors has in terms of shelf life. So what shelf life means is after you have made a chemical, so you've made up your hematoxylin, how long will it last sitting on the shelf before you can use it or before it's too old to be used? Some say that it has a shelf life of 2 to 3 months. Others say, it's got, as long as the bottle is closed, yeah, it'll last there for years. Yeah. Me, I say it'll last for years. Yeah, in fact, most of your hematoxylins will last for years as long as you don't overexpose them to sunlight. Now, Mayors hematoxylin is always used progressively. It's the one that gives us the latitude, yeah, to, bring that coloration into the nuclei and then wash it off. It doesn't have the affinity to overstain a tissue, you know, meaning that it doesn't have the affinity to attach to the cytoplasm. It doesn't have the affinity to attach to your connective tissues. Then we have Ehrlich. Again, our mordant is aluminum. Are you seeing a trend here? So yeah, most of the mordants in terms of hematoxylin are aluminum. Yeah, Ehrlich, it needs to be oxidized either naturally in the window or you can use sodium iodate. Yeah, you kind of have to be a little bit careful with Ehrlich. Yeah, because Ehrlich is more blue. It's more of a brighter blue than it is a purple. And if you over oxidize it, it turns into this like really light staining sky blue. Yeah, and that really light staining sky blue, when we apply a counter stain or a background stain, tends to disappear. So you sort of have to be a little careful with Ehrlich. Yeah, it has a natural ripening to it, yeah, which is about 2 weeks. Yeah, And it's used both progressively and regressively. Yeah, and it has a glycerol stabilizer in it. Then we have gills. Now, gills can be used both for histology, staining the nuclei, and cytology. So, it has the affinity for the actual tissue itself on the slide, but it also has the affinity to stain independent nuclei within a fluid, okay, which is what cytology is all about. Now, the really cool thing about Gill's hematoxylin is that it is the only hematoxylin that will actually stain goblet cells. If you're using Gill and you look inside of a goblet cell, you can actually see the mucosa, I'm sorry, the mucin that's inside of those goblet cells, where the other hematoxylins will not stain the goblet cells. So again, its mordant is aluminum, its oxidizer is sodium iodate, yeah, and it can be used in both staining situations. So it can be used progressively and it can be used regressively. Then we have Weigert's. Now, Weigert's is that special stain hematoxylin. It's never used in an H&E. There are two stock solutions. There's a solution A and a solution B that are mixed together to make your working solution. Carson is going to throw you for a loop with this because throughout the book, she will tell you that so there's these two solutions that you mix together. One is hematoxylin, and then one is your sodium iodate and your ferric chloride. The I was always taught that solution A was the hematoxylin and that solution B was the ferric chloride solution. Throughout Carson, she will flip-flop those back and forth. So she will tell you, oh, solution A is hematoxylin, solution B is ferric chloride. But then in the next chapter, she will tell you solution A is ferric chloride and solution B is hematoxylin. I don't know why, but that's Carson, right? We're going to develop a love-hate relationship with Carson. And so it's sort of confusing. If I were you, I would always simply remember that A is hematoxylin and B is ferric chloride. I do believe that in the textbook, there are multiple places where she flip-flops them. So keep your eye out for that and don't let her confuse you. So the ferric chloride that I just mentioned, which is solution B, is the mordant and the oxidizer. So it's one chemical that is doing two things for you. Okay. Now Weigert's has this extreme over oxidation sheen that happens. So you'll flood your slide with Weigert's and within 15 minutes or so, what will happen is you will see that the solution itself has actually evaporated out and it leaves this big black ring on your slide. And the sheen will appear like a green oil slick over the top of it, and it happens really quickly. I mean, we're talking 15 minutes as opposed to the sheen that will develop on Harris in 2 days, right? So you have to sort of watch out for that. It will give a black coating onto your slide. And There are ways to differentiate that out. But the easiest thing to do if that happens to you, some pathologists will look at that black coating that has happened on your slide and will refuse to read the slide thinking that something is wrong. But one of the ways that you can get around that is to simply take a chem wipe and wipe off the black that's attached to the actual glass of the slide. And then you can look at your Weigerts microscopically coming out of water. Throw it underneath the microscope and make sure that the tissue itself isn't overstained with Weigerts, before you submit it. Then we have Celestian blue. So Celestian blue is a replacement for hematoxylin. Celestian blue is not natural. It is a man-made chemical nuclear stain, and it does not come from the log of the barkwood tree. The whole reason that Celestian blue was developed is because throughout the years, we have engaged in shortages of hematoxylin. So in the 70s, we wound up with the environmental brigade, if you will. So people started recognizing, the destruction of the trees and the destruction of, our waters and those sorts of things. So what happened, is environmentalists started tying themselves and chaining themselves, to the logwood trees, thinking that hematoxylin came from the actual cutting down of those trees. Excuse me a second. Ah, when in fact, we weren't cutting down the trees. We aren't cutting down the trees. What they do is they peel the bark. The bark sort of scales off of the trees, and they peel the bark off of the trees, which doesn't hurt the trees. The trees keep growing and it grows new bark. But when the environmentalists tied themselves to the logwood trees and, did the hand-holding thing, not letting people go in and quote unquote destroy the logwood trees, we wound up with a hematoxylin shortage. Then come 1994, one of the big things that happened, sorry, in Arizona, I have allergies really bad. Anyway, in 1994, what started happening was in the 80s and the 90s, all of the cartel and the cocaine cartels sort of, came into play, right? And the thing about hematoxylin or the logwood trees is that they grow in South America. Okay, so everything is sort of shipped in via South America. When the cartels became popular, the big cocaine cartels, what happened was they didn't want people that were in their zones, so to speak, to collect the bark of the logwood tree. So then again, we had another shortage of hematoxylin. In 2009, and So let's see, in the 90s and the 80s, yeah, the cartels didn't want, you know, Americans basically, yeah, collecting the bark. So what happened was the cartels took over the plants that process the bark of the logwood tree. So from the 90s up until 2009, they were in charge, basically. The cartels were in charge of the plants. Come 2009, um, America, yeah, then went back into South America and took back over. There was a battle, between the Americans and the cartels. And the cartels finally said, okay, you know what? We don't want anything to do with this anymore. It's, not that we're not making money. We're spending too many resources sort of battling the logwood tree. And so they sold back the plants to the American people. Well, it took um, a couple of years there to make that transition happen, to remove the cartels out of the factory and out of control and bring the Americans back in to the factories to control the factories. So then again, we wound up in a shortage. So during these shortages, yeah, us supervisors were, calling each other up, right? Hey, do you got any backlog of hematoxylin that you can sell to me? I'll buy a gallon of your hematoxylin, that kind of thing. Nope, I don't got any, but I hear that this guy's got some. Yeah. So we sort of bounced. Sorry. So we sort of bounced around, one of us would, ooh, I got a hold of 6 bottles of hematoxylin. And so, we'd share with our friends. And then a next supervisor would go, ooh, I got a hold of 2. Here, I'll pay Becky back. And then I'll let you, borrow half of my other gallon, during these shortages. So we finally came up with Celestian Blue. That's sort of our backup now. And Celestian Blue, again, is 100% chemical. It's not natural. But the problem with Celestian Blue is it's a really, really light blue. It doesn't stain that deep purple color. It stains more of like a sky blue color. So it's really hard to I mean, it looks beautiful if you get it right, but it takes a lot of work up to get it right to create that differentiation between the nuclear staining and the cytoplasmic staining. So speaking of cytoplasmic staining, when we talk about cytoplasmic staining, we're talking about eosin. Yeah, so there's all kinds of different types of eosin as well. Yeah, there's eosin Y, there's alcoholic eosin, there's eosin with floxine. So eosin Y, um, I mean, one isn't greater than the other. They all produce the colors that we want, but they give off different shades. So eosin Y is on the sort of lighter pink arena. Alcoholic eosin is sort of the middle arena. And then floxine is an additive that we can put in either one of those two that actually brightens the pink level up, right? So with eosin, our best staining will occur somewhere between 4.5 or 4.6 to 5 pH. If you let it drop, however, down below 4 pH, we're going to get a thing that's called non-specific staining. And non-specific staining means that whatever dye it is that we're using has a target. So eosin, right? Cytoplasm, connective tissue, and red blood cells. Those are our targets. If we let it drop below 4, it's going to start to tag and stain other things. So it's going to start to interfere with our nuclear stain, our hematoxylin stain. It's going to start to interfere because it's going to start, staining extracellular materials like elastic fibers. Okay. So it sort of muddles everything up. Makes it that stain, your stain should be nice and crisp and distinct underneath the microscope. Where if you wind up with non-specific staining, it sort of flat bases everything microscopically. You start to not be able to tell between the 3 structures of the, cytoplasm and the connective tissue and the red blood cells. They all sort of blend together as opposed to having those 3 distinct colors, for those 3 distinct tissue types or cellular structures. We always want 3 very distinct eosin colors. So again, remember, your connective tissues are the lightest. Your cytoplasm is the middle pink, and then your red blood cells should be a real bright, vibrant pink. So the H&E stain itself, nuclei are going to be blue to purple to black, okay? Your cytoplasm is going to, and your connective tissue and your red blood cells are going to be those 3 distinct shades of pink. And then your chromatin, the chromatin is inside the nuclei, inside that cell, and it's got like this salt and pepper effect inside the nuclei. Chromatin is DNA and RNA. Okay, that's the word for the DNA and RNA combined together. So it should be this nice, beautiful sort of salt and pepper granulation, and be very visibly seen. Okay, you don't want your nuclei to be so dark that you can't see that salt and pepper effect. Now, there's terms that you need to know in regards to the H&E. Differentiation. Differentiation is used in regressive staining, and it is the chemical that I should say the solution, that is removing the mordanted hematoxylin from the tissue to the desired intensity. So remember that when you are staining regressively, you are overstaining the tissue with hematoxylin. But then you have to use a differentiation solution to pull out the hematoxylin, leaving only behind the nuclear staining. Then there's this thing that's called bluing. So if you've stained your tissue or you've stained your nuclei with hematoxylin, if you took it out of water afterwards, so it goes hematoxylin and then into water, and you pulled a slide at that point and you looked at it underneath the microscope, the nuclei would be a red-brown color. We don't want that red-brown color because we want to have a color that contrasts against the pink color. So imagine a red-brown color and a pink color sort of being together on one slide. You're not going to see that contrast between the 2 colors. So we have to change the color of the hematoxylin. It's going to come out a red-brown color, okay? But then we apply what's called a bluing solution. And the bluing solution is the act of turning that red-brown color into that deep purple color, okay? And bluing solution is extremely alkaline. And so because of its alkalinity, when we are running slides through the H&E stain, that is the spot, that is the chemical that will, if left too long, will lift your slide, your section off your slide. Your section's going to start lifting away from the slide. And if you leave it too long, your section can actually wash away completely. So the trick is to find the right depth of hematoxylin, yeah, so that you can pull the excess out with a differentiator and not have to leave it soaking into a bluing solution for a very long time, because you're going to leave your it's called wash off. You're going to wash off your section. Then we have depair. So depair is deparaffinization. Depair is when we remove, think about it, right? When we pick up a slide, we still have the paraffin in the slide, right? Yeah, we bake it to get rid of the excess, but it's still within yeah, it's still within the nuclei and the cell wall of your tissues and your connective tissues and all that kind of stuff. So we still have to pull out the paraffin that's existing within the tissue structure. And we do that with xylene. And so that's what's called deparaffinization. We have to pull that out in order for us to attach anything else to it. If we still have paraffin left in our section, we're going to have overall light staining or little to no staining at all. Then we have this thing that's called hydrate. So hydrating is returning the tissue back to its water state, okay? Just like in processing. Yeah, but because we've processed and we have this paraffin in there, we have to pull the paraffin out, and then we want to return the tissue to the water state like it would be in the human body. So we do that by going through gradations of alcohols. Yeah, so we start with 100 and we graduate down to a 95. Yeah, and then we hit it with water again. Now we've returned it to the point where we can actually stain something. Then there's dehydration. Yeah, so dehydration is when we are going the opposite direction. We are removing the water. So it goes like this. It goes deparaffinization, then we hydrate to water, okay? Then we run our stain. When we're done with our stain, we still have to cover slip it. And so what is mounting media? It's xylene based. So we have to take it back to the availability of xylene. So in order to do that, we come out of water and we go into gradations of alcohols. We go into 95s, we go into 100s. Then we can go into xylene, because remember, xylene and water are not miscible with each other. So we have to take it to 100% alcohol, yeah, and then into xylene. And we have to make sure that we don't have any carryover of that water from the 95 into the 100s.
Unknown caller.
Carryover of water into the 100s, which would then carry over into the xylenes. So that's sort of what we're doing there. It's depair, it's hydration, then it's our stain, then it's dehydration, clearing, and mounting. And clearing is our xylene. So, quick explanation. We have depair and hydrate. Okay. So the depair is a couple of changes of xylene. Then we hydrate to water. So the hydrate is a couple changes of 95 and then a couple changes of 100. And then, no, it's the opposite. The hydrate is we go from xylene to 100, a couple changes of 100, and then a couple changes of 95. And then we wash the slides in water to get rid of the alcohol. From there, we're going to go into our hematoxylin. That's going to be our nuclear stain. After we come out of hematoxylin, we're going to water wash the excess hematoxylin off of the slide. Then we're going to go into differentiation solution. That differentiation solution is going to pull the hematoxylin out of everything else in our tissue except for our nuclei. Then we're going to go into water wash, and that water wash stops that differentiation from happening. That's a really important water wash, yeah, because if you don't leave your slides in water long enough, then you're going to leave a little bit of differentiation solution on your slide. If it's left on your slide, it will continue to differentiate throughout the remainder of your stain. And it's going to continue to lighten up your nuclei. Okay, and we don't want that to happen. So you want to make sure that this water wash is a good water wash, a good long water wash. Then we're going to go into bluing solution. So we are going to change from the red-brown color to the purple color by bluing it. Then we're going to water wash again to remove that bluing. This is another place where you need to make sure that your bluing is washed off of your slide. If you don't, it will continue to blue throughout the remainder of your stain. And you're going to get it darker and darker and darker. Okay, so this one will continue to lighten up your nuclei. The bluing is going to continue to deepen your nuclei. And in the end, when you look at it microscopically, you're going to have an inappropriate H&E. So be careful when you're done with this water wash. Be careful with this step. Some people will let you do it. The majority of people out there are doing it, because the majority of people, at least locally, are my previous students. But I always went into an 80% alcohol. And the reason I would go from this water wash to this 80% alcohol is because eosin is alcohol based. So I would go into an 80% alcohol to sort of introduce the alcohol to the slide, to the section, so that when it hit the eosin, it would readily absorb the eosin, as opposed to leaving my slides in eosin for a long time waiting for it to absorb. It helps that eosin uptake into the tissues. And then you're going to dehydrate. So you come out of eosin and you go right into a 95% alcohol. That very first 95% alcohol is a differentiator for the eosin. So if you look into the stainer, you'll see that there's sort of this drag of eosin coming, when you come out of eosin, there's a drag of it goes sort of from an orangey color, which is the eosin. And then the first change is, got a lot of eosin in it. And then the next change of 95 has it's sort of less eosin in it. Those 95s are the differentiator for the eosin. Those 95s are what's going to give you the 3 independent colors that you're looking for with the H and E. Then you're going to go into 100, because 95s have 5% water, and we can't get to xylene because xylene and water don't mix. So we have to go into a couple of changes of 100 and then into xylene, which is our clearing, okay? From our clearing, we are going to then mount our slide, meaning we can cover slip our slide. Depair and hydrate, and this last step on the other end is called DCM, okay? Dehydrate, clear, and mount. Next quarter, not this quarter, I will accept for anything that you write up, depair and hydrate and DCM. But for now, you have to write the whole thing out, okay? And we're going to walk through these. So deparaffinization, which is the very first thing that we do. And that's removing that paraffin that is still within the tissue, okay? And we're going to do that with xylene. So I go through 3 changes of xylene, okay? My very first change of xylene is 10 minutes. And the reason I soak it in 10 minutes is because I want to loosen up all of that paraffin that is embedded still within the tissue. Then I'm going to go into a second change of xylene. There's going to be a little bit of drag coming over. So my second change of xylene, I leave in there for 3 minutes. And I add a third change of xylene, because I use that third change of xylene as a safety net. By the time I get to that third change of xylene, I know that that xylene is actually clear and clean, so that I can move on without leaving behind any type of paraffin in my section. Now, all of the paraffin has to be removed from your section. Otherwise, you're going to get this splotchy, irregular looking stain and this sort of overall decreased flat intensity. Now, some hints to depair. Make sure, you guys, that when you're going through the buckets, that the level of the xylene is above your tissue. If your xylene is dissipated out and your tissue is this big and you're only hitting this much of your tissue, this upper half of your section is not going to stain well, okay? When you put your slides in the rack to stain, make sure that they're not doubled together. Meaning if my palms of my hands are where the tissue is on the slide and you rack those slides and they go like this, guess what? They're not going to stain because they are not exposed to those chemicals. You need to leave your slides, your sections exposed. Watch out for discoloration of your xylene. Yeah, especially, the first bucket of xylene. It'll turn sort of a yellowy color. And once it does turn sort of a yellowy color, that is your indication, that you need to change it out. Because it's now saturated with paraffin, and it can no longer pull paraffin out of your section for you. Now, because of this, we change and rotate daily in the workplace. But in your lab, you need to, there's a, uh, a chart, a log that you need to fill out whenever you change anything on the processor, so that the next guy that comes along can look at that log and go, oh, okay, there's fresh xylene, or the hematoxylin already got changed today, or filtered today. So yeah, stay on top of it. Stay on top of that log, and stay on top of your chemicals. Now, at first glance, new students will think that they have to change out those 95s after the eosin, yeah, because they have color drag in them. That's not the case, okay? We know that there's going to be drag of eosin, because in those 95s, that's exactly what we want them to do, is to differentiate out those eosins. So our hydrate to water. So we've deparaffinized. Now we have xylene on our slide. So now we have to get it back to water. So this is a series of gradation of alcohols. The very first one has to be 100%, because remember, water does not mix with xylene, or yeah, water doesn't mix with xylene. So you have to make sure that that's a 100%, okay? Now, the most common sort of hydrate to water is 2 changes of 100%, and then 2 changes of 95, and then a water wash. Now you can do this in multiple ways. I mean, some may go 100% to a 95, to an 80, to a 70, to a 50. But by doing this, it forces you as the HT to actually make continual gradations of alcohols, where if you're doing it this way, you can just make a big batch of 95, and it's only one gradation that you have to make. Now, you may see this gradual change happening in research with very, very delicate tissues. In your normal operating histology labs, you're not going to see that many gradations. Now, if your hydration is not done properly, again, you're going to have this overall interference with the hematoxylin staining. You're going to have xylene carryover into your droplets of into the alcohols. And you will know if your depar and hydrate is not done correctly. It's an instant in your face, oh my gosh, I didn't do that right. If your slides hit water and they turn milky white, it's game over, okay? Now you have to take them all the way back to xylene, and then xylene back forward. So if you ever see that milky white happen when you hit water, your hydrate to water was not done correctly. So now we've hit water, right? Our very first, we've gone through paraffins, we've removed our paraffin, so we've gone through deparaffinization with xylene. Then we've gone through a couple changes of 100. Then we've gone through a couple changes of 95. Now we have to wash the alcohol, remove the alcohol off the slide. So there's this thing that's called window painting. And you want to stay in that water wash until the window painting goes away. And so what window painting is, and this occurs all the time in staining. What window painting is if you look at your window when it's raining outside, and you know how you see this sort of iridescence of the rain coming down the window, that is window painting. So you have to keep washing that slide until the window painting goes away. And that's an indicator that you have completely gotten the alcohol off of your slide. And again, if you still have alcohol left on your slide and you move forward with your H&E, you're going to get this splotchy staining. So then you're going to go into hematoxylin. Yeah, and that's going to be your nuclear stain, more specifically your chromatin. That's your salt and pepper effect inside of your nuclei. Now, there's some causes for poor hematoxylin staining. Your tissue could have autolysis. You could have poor fixation. You could have overfixation. You could have incomplete depair. You could have over decaled something. Yeah, the big one is improper staining time, and you guys are going to learn this in your labs as you're working up your H&Es. Maybe your differentiation was too short. Maybe your differentiation was too long. Maybe your hematoxylin is over-oxidized, and I just explained to you how to test your hematoxylin. Maybe you have some water contaminants. Maybe the water is too acidic, and the tap water is too acidic, and you have to account for that. Maybe the sections, the microtomy section was way too thin. Maybe you have an incorrect pH on your eosin. Maybe you didn't remove all of the clearing agent during hydration. Maybe your water washes weren't long enough and you had window painting remaining. So after your hematoxylin, you're going to go into that water wash. You're going to remove the excess hematoxylin, and then you're going to differentiate. So differentiation solution is an acetic acid solution or a hydrochloric acid solution. And it's used, okay, the differentiation step is used during the regressive staining in the H&E. And it's going to remove any hematoxylin or blue tinging non-specific staining out of everything in your section except for your nuclei. After your differentiation, you're going to go into water wash number 2. So this is going to remove either the acetic acid or the hydrochloric acid that you use to differentiate. It's going to remove the acid from this section. So this is what stops that differentiation process. And remember that if it's not done correctly, differentiation will continue to occur throughout the remainder of your slide. And your nuclear staining is going to get lighter and lighter and lighter as you continue. So really important water wash here. Then you're going to blue. So bluing is an alkaline solution. Again, the original aluminum hematin lake of hematoxylin is red. And so when you blue it, it's going to convert that red into the desired purple lake that we want. Now, when it's red, it's soluble at a pH of 5, okay? When we hit it with the blue, it also makes that hematoxylin insoluble in most cases, okay? So there are things that you can do in terms of special staining that will pull it, but in most cases, we've made it insoluble. So what is bluing? There's commercially made bluing that you just purchase, but the reality is it's really just an alkaline solution. It could be sodium bicarbonate in water, yeah, or it could be ammonium hydroxide in water, okay? You can even blue with a very excessive water wash number 2, a long water wash number 2. But we don't want to delay patient results, right? So therefore we employ the bluing step when we're talking about H&E. Now, it's important that you understand this, because this traps people all the time, when you're working up an H&E. It is not possible to overblue a section. It cannot be done. You can only blue the section for the amount of hematoxylin that you put into that section. So you can't fix a weak hematoxylin stain by increasing your bluing. If you're giving, if you're sitting in a hematoxylin for 10 minutes and then you differentiate and then you go to bluing and it's not turning, you can't say to yourself, I'm just going to stay in bluing for a longer period of time, because you didn't give it enough hematoxylin in the first place. Okay, so it can only blue up to the amount of hematoxylin that you gave it to blue. Okay, so you cannot theoretically overblue a section. Okay, if your stain is not blue enough, you need to increase your hematoxylin, not increase your bluing. Okay, and you can visibly, when you're doing this in the lab, you can visibly see the change happen from that red-brown color to that purple color. So keep your eye on your slides, on that section, so that you can see that reaction happen. And then you're going to go into water wash number 3. And this is going to stop that bluing process from happening. If you're FYI, here's a tip to help you guys when you're in the lab. Hematoxylin stops penetrating after 7 minutes. Okay, so if you say to yourself, I'm going to go in hematoxylin for 7 minutes, and then in the end, your hematoxylin isn't dark enough, don't try to increase your hematoxylin, because it's not going to penetrate any more than it already has. So that tells you that it's either your differentiation step that needs to be adjusted, or it's your bluing step that needs to be adjusted. Okay. And again, if you don't stop this bluing from happening, it's going to continue to blue throughout the remainder of your stain, and you're going to wind up with a really dark nuclear stain. Now, again, this is a Becky step. So I go into that 80% alcohol. That introduces the alcohol back into the section to allow the eosin to absorb into the tissue more readily. And the reason it does that is because the eosin is an alcohol-based stain. So then you're going to go into eosin. This is your cytoplasmic stain. And it's often referred to in Carson as a counter stain, because it's the counter stain to the nuclear stain. Okay, and this is your 3 shades of pink. Now, there's causes for poor eosin staining. Maybe your pH is too high, maybe your pH is too low. The alcohol steps after eosin, if you leave, because remember those 95s are your differentiation solutions for your eosin. So if you're in those 95s too long after your eosin, you're going to pull your eosin out. Maybe you've got some contaminated alcohol after your eosin staining. Maybe you have excess carryover from other solutions going into your eosin. Maybe you have a thin section. Maybe you didn't stay long enough in your eosin in the first place. Also, uh, watch your eosin level because eosin is alcohol based. Um, Alcohol evaporates. So if it's evaporated out, then your eosin, the alcohol is evaporated out, then your eosin is going to be brighter than you want it to, and you're consequently going to have non-specific staining. Maybe isopropyl alcohol was used in your stain line. If you remember back to fixatives, we talked about this, that this is the whole reason why a lot of labs use denatured alcohol, is because it goes in stain lines as well as goes in processing, where isopropyl alcohol is not miscible with eosin. So the eosin won't dissolve in isopropyl alcohol, and so therefore that staining solution is inappropriate. Maybe you left it in there too long, or maybe you have poor fixation happening. So after your eosin, now you need to dehydrate. So I go through 2 changes of 95s. That's going to start the dehydration process and differentiate your eosin. Then you're going to see 2 to 3 changes of 100s, just because we know we have that drag, right? So we want to make sure that the final 100 is a true 100. Let's see. Yeah. If you go too short in these dehydration steps, that water is going to drag quicker all the way to your xylenes. So you want to make sure that you're in them long enough to not have a whole bunch of drag, but short enough in your 95s, that you don't over differentiate your eosin. Then we're going to go into clearing. So clearing is 3 changes of xylene, for a minimum of a minute each. This is going to pull all the alcohol off of your slide, and it's going to allow your slide to have a film of xylene, so that it's miscible with your mounting media. Now, if you don't get all the alcohol off of your slide through your clearing agent, your eosin is going to continue to differentiate, and it's going to bleed out of your section in between the cover slip and the slide itself. If you hit your clearing agents and your slides turn milky white, guess what? You have water drag all the way through your alcohols. So you've drugged that water all the way into your xylenes. So keep an eye for bubbles on the bottom, like little, they look like little oil slick bubbles, vinegar and oil kind of effect in the bottom of your clearing xylenes. If you see that, that's water sitting on the bottom of your container. Now, water, if you cover slip with a xylene that has water in it, when you look at it microscopically, it's going to be all bubbly. There's going to be little, sort of looks like a trickling stream Okay, there's going to be all these little bubbles sitting all over the top of your section. Now my friend Rex, I don't know if you guys have met Rex yet. His name is Rex Johnson. Yeah, he's the creative waste guy. He's the guy who supplies us with all of our alcohols and xylenes. And he makes these little, they're called water catchers, and they sit in the bottom of your xylene. Yeah, and they absorb the water out of your xylenes. And it's sort of a safety net kind of thing. I don't I don't know that we have any left in the lab, but you might try to convince Jazz to get them. But the reality is not everybody's going to use those. They are going to rely on their histotechs and their histotechs education, as and their stain logs, to assure that all of their chemicals in their H&E line, are accurate. So now you're ready to cover slip. So again, that's called DCM. But you can't call it DCM just yet. You have to step it out for me. So quality assurance, some tidbits. Yeah, keep your hematoxylin covered when it's not in use. That way it will avoid over-oxidation or ripening of your hematoxylin. Check your clearing xylenes often. That's front and back, deparaffinizing xylenes and your clearing. Because you need to check your deparaffinization xylenes to make sure they're not saturated with paraffin. And you need to check your clearing xylenes to make sure that there's no water bubbles sitting on the bottom. Follow your lab's procedure for discarding and rotating solutions. Again, this is that log. That log lives right next to the stainer, and you should be checking your solutions, either discarding them, rotating them, or filtering them every morning. Okay, your eosin, your hematoxylins need to be filtered every morning. And then everything else needs to be looked at before you can run anything on your stainer. Now, remember, we've talked about this. Remember, don't forget about corn flaking. Okay. The minute that your slides hit that very first deparaffinization xylene, you cannot let them dry out at any point until they're done being cover slipped. If you do, you're going to wind up with that corn flaking, and that's when the cells curl up on the sides, and the doctors just can't read that. Okay, it makes that particular section unable to diagnose. So yeah, quality control, you got to check it daily. First tech in the door, I did it this way in my lab. First tech in the door was the QA guy. They would filter the hematoxylin, they would filter the eosin, they would rotate the 95s and the 100s. They would check the whole line. Now, in an operating lab, you have to have an H&E control to prove to the docs that your H&E is spot on before you start staining any patients. So in my lab, I love placenta as a control. So we would take a placenta slide, and after all the chemicals were cleaned and everything was documented, we would first thing in the morning throw a placenta slide on the stainer. And then either myself, or as the supervisor, myself or my lead tech would take a look at the H&E to make sure that we were seeing everything we needed to see, and then your patients can follow. Okay. And again, everything has to be logged. Even your whoever it is that read the H&E that morning and said, this is a good stain, let's move forward with patients. You have to log that you approved that stain. So now we're going to look at some slides here, some pictures, yeah, so that you guys can start noticing what's a good stain and a bad stain. So here we have a really nice stain. So if you look at these columnar cells, you can see the cell wall and you see the granulation, or the nuclear wall, I should say. And you see the granulation factor happening inside. There's that salt and pepper appearance, and then you can see the nucleolus as well. Same, if you look at each one of them, you can see that same effect. Okay. So this is beautiful hematoxylin staining. Now, as for the eosin, well, it's not so great. Yeah, it's really light. Here, over here, see here, here's some goblet cells over here. See how they're not stained. And remember that they shouldn't be, because the only hematoxylin that stains goblet cells will be your Gill's hematoxylin. Okay. Your eosin here, well, I mean, you've got 1, 2, sort of 3 shades of pink. Are they dramatic? No, they're sort of monochromatic. We would like to see them really have a separation incline in between each one. So nuclear detail, beautiful nuclear detail. You can even see, this is why I love placenta so much for an H&E control. So right here, if you remember back to your biology, remember the different stages, you've got a nucleus. The first thing that happens, the nuclei sort of go to each side, the nucleolus goes to each side. Then it starts to enclave, then it enclaves all the way, and then they pop apart and they have 2 brand new cells. So if you look here, you can see that enclavement starting to happen here. Yeah, and this is placenta, and so the reason that I love placenta is because it's a fast growing organ. And because it's a fast growing organ, you can see all sorts of replication stages in the placenta. So plus it's blood rich, right? So I love to use a placenta as my H&E control. Now here, the nuclear hematoxylin is really dark. So if you look into each one of these cells, you can't see that chromatin, that salt and pepper. You see a little bit of it over here. But when you look at all these cells, you can't see that. And because the hematoxylin is so overpowering, it's even muting out the red blood cells and the cytoplasm. So if you are struggling with your eosin staining right off the bat, in terms of when you start working up the H&E, always work up your hematoxylin first, okay? Never start working up an H&E starting with your eosin, because once you get your hematoxylin done, your eosin will follow. But if you try to work up your eosin first, then go to the hematoxylin to work it up, you're going to mute out your eosin, because it's no matter what you do with the hematoxylin, it's still going to affect the eosin because it's down the line. Okay. Yeah. So do we have 3 shades of pink here? Well, we kind of got one there. We got one here, and we got sort of one here, but look at the purple hue to the cytoplasm. Okay. We don't want that. So here, your nuclear staining is just lost. The nuclear walls are not being stained appropriately. You can barely see some of the nuclei. This is over differentiation. Okay, it's either over differentiation or there isn't enough time or enough penetration by the hematoxylin in the first place. Now this is obviously, I mean, look at this. You cannot even see into the cells. This is placenta again. This is way, way muddy, dark hematoxylin. So either we overstained with hematoxylin, under differentiated. Okay. Again, here's overstaining with bleeding. So you can see how some of these cells look good, but some of these cells look good. But then if you look here, there's hematoxylin bleeding in between the cells out into the cytoplasm. Okay. And again, that's really poor staining. We need to have our hematoxylin within our nuclei, not bleeding out. So this is an obvious thing as far as workup goes. This is under differentiation. So another one of bleeding and poor differentiation, if you look at your cytoplasm, it's got a purple hue to it. Your hematoxylin is just bleeding out of your cells and into your cytoplasm. Now, this is actually lymph node, and lymph node has its cells are a little condensed, if you will. And this is on low power, but so the hematoxylin staining, if we got up close and personal, it might actually be okay, because it is lymph node. But if you look at where your eosin is supposed to be, there's just no eosin there. Okay, so this is poor hematoxylin staining or poor eosin staining. Now, this is a really great thing for you guys to know and really sort of pick up on right away, because it will affect your staining in every single stain that you do. This is actually a very thick cut section. So you can tell that because when you look here, the cells are stacked upon each other. Okay, they're sitting on top of each other. They're overlapping each other. So remember that we cut at 4 microns because 4 microns is the thickness of one cell. So if you're pushing on that downstroke, if you're pushing too rapidly with that arm, you're creating thick sections. So 2 things here. At microtomy, you need to look at that water bath with that section on it and recognize that it's a thick section because it will appear more white than the rest of them. And then, of course, when you stain it and you look in the microscope and you see all of these cells laying on top of each other, you know instantly that this is a thick section, and this cannot be read because the pathologist cannot discern any of the replication factors. So this is staining with unfiltered hematoxylin. So like this right here is a nuclei. But when you start to look deeper and closer, you see these little tiny specks out here. And there's a speck there and a speck there and a speck there. Those are not nuclei. And here's another one here. This is unfiltered hematoxylin. This is when your hematoxylin has over-oxidized. Here's your goblet cells. So this is stained with Gill's hematoxylin. So if you look inside of these goblet cells, you sort of see this light purple mucinous staining in there. And this is the only hematoxylin that will do that. The end. Questions? Anybody still there?
I have a question.
Okay.
Sorry. So, so with these, we're using so we're putting them in racks with the hand staining or special staining, right? So when I'm just going through my brain. If we're doing that and say we're short on time, which hopefully we aren't, but if we are, is aggregation something that can help with this, like it is with fixing or when we do hand processing? Will that speed it up?
Absolutely, aggregation will. That's why when you see the stainer going, it comes up, it goes over, it drops into a bucket, right? But then every once in a while it'll go like this. It's aggregating your slides for you. Okay.
Okay.
Yeah, you betcha. Yeah, and so when you guys start working up your H&E, I'm not talking about you working it up on the stainer. You guys are going to have Copeland jars of your solutions, and you're actually going to hand stain your H&E. Moving your own slide from one to the next, to the next, to the next, working up your H&E. But yes, you can, in fact, stand there and do this and dip it. Okay. Part of the problem with aggregation when you're hand staining is that it's never the same. You know what I mean? So you can stand there and you can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then move on. But you need to make sure that you're at least doing it the same way the very next time. Does that make sense?
Yes. So you have to make sure you're being consistent in your aggregation techniques because we're not
Yes,
robots, but we need to be like robots. So it's consistent.
correct.
Got
That
it.
is,
Thank you.
you're welcome. Sarah, what's up?
I was gonna ask, are we going to be able to try out the different types of heme, or is it more just for testing?
You're doing 3 different types of hematoxylin. That's your lab. You're going to work up
Um,
3 different types of hematoxylin.
are we choosing, or is it a specific three?
No, you get to choose from whatever the hematoxylins are available. Okay.
Sweet.
I don't think we have like Ehrlich or, it, most of our hematoxylins are going to be a Harris hematoxylin, but we have all sorts of different types of Harris hematoxylin. So you'll pick 3 different Harris hematoxylins from 3 different manufacturers. They're all going to stain different. They're all going to have just a little bit different hue to them. But yeah, you're going to work up 3 independent H&Es. And you know
And
what?
is
And get this, once you get your first one worked up, your eosin will probably follow into the next one and into the next one. Does that make
okay.
sense?
Yeah.
Okay.
And I guess just my last one was, is Celestine blue on that list, or is it just a in case we run out?
Yeah, Celestian blue is only made in case we have a hematoxylin shortage. I don't think there's any Celestian blue in there. You could look and see if we have the powdered Celestian blue. But I don't think there's, well, I don't think there's any Celestian blue solution made. Yeah, but we might actually have some powdered Celestian blue that you could make Celestian blue with.
Thank you.
Jazz can help you with that if you find it. Good? Did I answer your
Yeah.
question? Okay.
Thank you.
Skylar, what's up?
Hello. I was just wondering, you said that you like placenta as your test tissue. Is there any tissues that you would recommend not using as the test tissue?
Yes, there's many I would recommend. Yeah, let's see. And it's just a FYI, let me correct you a little bit. It's called a control tissue, not
Okay.
a test tissue. Okay, it's called a control. Yeah, and yes, I would not recommend when you choose your control tissue for your H&E, you want to make sure that you have a tissue that has a a lot of cytoplasm, a lot of connective tissue, and a lot of red blood cells, as well as nuclei to stain. Now, the tissues that are like really compact, such as lymph node, pancreas, kidney is sometimes used as a control, FYI, Andy. But you really want sort of a tissue type that has that cytoplasm, and the three components and the nuclei uh, variable, right? And available, because not all tissues have, like, not all cell types have large cytoplasms. So that's why I choose placenta.
Perfect. Thank you so much. And I will correct that on my notes.
Yeah. Andrew, what's up?
All right. So I see for the hematoxylin that you said we can do oxidation either through like chemical oxidation or we can just do natural.
Mhm.
Is there like so I see Delafield, we really only have the option for natural oxidation. So there's like we can't use chemical for Delafield. Is that it?
Well, you probably could for Delafield. You could use a sodium iodate. But what happens with Delafield is that it muddies really quickly. So it would be sort of iffy to actually
Okay.
chemically oxidize it, because it likes to be oxidized in a slower process, as opposed
Okay.
to hitting it hard with a sodium.
Okay, so I see they're just like kind of like recommendations, but you can oxidize it either way. It just kind of depends, I guess.
Yeah, it
Okay.
just kind of depends. I mean, it's kind of spaghetti. Yeah,
I
you
see.
have
Yeah,
to
that
be
makes sense.
really, really careful with some of them, as opposed to other ones like Harris loves to be oxidized with sodium iodate.
Mm.
Delafield does not prefer it. And you could screw it up easier. Yeah, but sure, you could try it. The
I
one
see.
thing that I would warn you about, and this is true, um, well, it's Carson again, yeah, but um, on your certification, if Carson says you cannot oxidize with Delafields with sodium iodate,
Uh-huh.
that's, it's probably not reality. But on your
Right.
certification, if that question comes up, you have to go with what Carson said.
Okay, that makes
That makes
sense.
sense?
Yeah, that makes sense.
Okay. Angel, what's up?
Going back to water wash number 3,
Right?
you mentioned that the hematoxylin stops penetrating in like 7 minutes. So basically, what would be like the
No,
ideal?
no. So hematoxylin doesn't stop differentiating
Okay,
in
doesn't.
7 minutes.
Okay.
Hematoxylin, when you take your slide and you put it into hematoxylin to stain with the hematoxylin, it only absorbs for 7 minutes.
Okay.
So
got
if you leave your, you think that you need to increase your hematoxylin, okay? You're working up an H&E and you think that you need deeper hematoxylin staining, but you're at that 7-minute mark, increasing your hematoxylin time, if you were going to go, oh, I want it darker, so I'm going to increase it to 10 minutes, it's not going to make a difference as far as absorption of hematoxylin. Between after 7 minutes, you can leave it there for 30 minutes and it's not going to get any darker. So it's if you are over dark with hematoxylin, if your hematoxylin in the end, you look at it microscopically and it's muddy, you need to increase your differentiation, not do you see what I mean? You could decrease your hematoxylin or you could increase your differentiation. But by leaving it longer in hematoxylin is not going to make a difference for you.
Makes sense.
Does that make sense?
Yeah, makes
Okay.
sense. Yeah.
Okay. Any other questions? Did you have another question, Angel?
No, I'm already done. I just trying to lower it down, but it's
Oh, okay.
okay.
Okay. All right. So that's the H&E. Okay. You need to know every single step in the H&E, and what each step is doing. So I'm going to share. Let me. Okay. So let me change my font. Can you guys see this?
Yes.
Yes.
Okay. All right. So the H&E, the very first step is xylene. The second step is xylene. For me, the third step is xylene. Oops. Now, this first step is depair, right? And I go for 10 minutes in that first step. And so this is removal. Paraffin. Oopsie doopsie. Now, your second xylene is continued. I don't know why I'm typing weird. continued depair, right? And that would be removal of paraffin. Now, your third xylene is safety. That's an insurance policy of the removal of xylene. Does that make sense so far? Yes?
Yes.
Okay. Next is your first 100%. So this is removal of xylene, right? Oops. This should not be xylene. This should be paraffin. This is going to be your removal of xylene. But this is going to have drag of xylene in it, right? Ugh. And this is going to have the most drag of xylene in it. Now, your second, oh, and yeah, your second 100 is going to be a cleaner. I'm still not typing right. Cleaner solution. Golly. The second change, right? Does that make sense? Give me a yes or a no.
Yes.
Then we're going to go into 95. This first 95 is intro to alcohol. I'm going to go ETOH. Intro alcohol, right? No. Intro to water, which then moves me right back up here to this, which is intro alcohol. But now we're going to have drag, right, of 100. So consequently, this is not a true 95. Then we're going to have a second 95, which is still intro water, closer to a true 95. Then we're going to go into water. This water is removal of alcohol. Watch. Watch for window painting to go away before you move on. Making sense? Anybody confused? Then we're going to go into hematoxylin. This is your nuclear stain. Then you're going to go into water wash 1. This is removal of excess heme. So you want your heme washed off your slide. And that's excess hematoxylin, that carryover that's going to be attached to your slide / glass. Then you're going to diff. This is going to pull excess non-specific staining of heme. Leaving nuclear stain of heme. Then you're going to water wash number 2. This is going to stop your diff, okay, and prevent further differentiation through remainder of staining. Then you're going to blue. That's going to turn the heme red-brown to blue-purple. And make insoluble. Then we're going to water wash again. This is going to stop blue. Now we're going to go through our alcohols the other direction, right? Oh no, now we need to go to eosin. Well, depends on whether you want to do a Becky step or not. We'll put it in there. And that would be intro alcohol. Then we're going to go into eosin. This is your connective tissue RBC cytostain. And it is ETOH based. Then we're going to go into 95%. This is going to diff the eosin. Diff eosin and begin dehydration, which takes me right back up to here. This is begin hydration. And if we want to even, let's see, we'll go here. And hydration. Then we're going to go into another 95. This is going to continue diff of eosin and continue dehydration. Then we're going to go into 100. Oops. This is dehydration. $100, but this guy here is also going to have water carryover. So not a true 100. This guy is continued dehydration. Ugh. Then you're going to have another 100. This is your safety. True 100%. Because xylene and water do not mix. Then we're gonna go into xylene. This is going to have ETOH drag. Not true. Not true. Xylene. Then we're going to have another xylene. Oh, and this is going to be start clearing. This is going to be continued clearing. And of course, I'm going to go on to a second page and I don't want to. So I'm going to do this. Then we're going to go into another xylene. This is a safety true xylene. And we want to watch for bubbles. Then your final xylene is your cover slipping xylene. So when you are asked to, let's see, begin hydration, hematoxylin, 95, begin, continue. And yeah. So when you are asked to give me a, write me up a H&E protocol, okay? And tell me what each step is, or you have to match them, or if this is what you're looking for, okay? Now, an entire protocol, I'll save this. I'll save that for you and post that for you. Now an entire protocol is completely different. So you guys need to, let me see, do I still have Canvas up? Oh, but I can get there quickly enough. Gotta find one. I know it's here somewhere. Let me find it. Hold, give me a second, guys. Let's see. Ah. Okay, so this is in year 120, and it's the hand staining H&E protocol template. If you look on your calendar, yeah, you're going to see that a group of you are going to be in special microtomy, a group of you are going to be in cytology, and a group of you are going to be in H&E workup, and you're going to switch around, okay? Those of you who are going into your H&E workup, this is an example, and you can just download it and fill it in yourself. But this is an example of a Gills hematoxylin protocol. This protocol, or I guess it's Mayer's, but it says Gills over here. So you'll fill it out yourself. So you'll have, all of this, and we'll talk about SOP writing in a few days here. You're going to have a control number, a slide. You're going to have the date. You're going to have which run number it is, what the tissue type is. Yeah, but then over here, you're going to have, okay, here's our procedure. Here's what we did. This actually looks like a, maybe not, but they don't have xylene up here. So you'll have to add that. But this is what we're looking for in terms of a protocol, okay? Not just a list like we just made. This template is here for you guys to use when you're working it up. So you'll go through your steps and how many minutes you went into each thing, whether you agitated, whether you didn't. And then down here is this little box that, says, ooh, insert troubleshooting. Well, what were the results? Oh, my results was muddy. So their eosin was muddy. So they're going to decrease their time in eosin. So then you go back and you make your adjustment to whatever it is that you determined was wrong with your slide. You make your adjustment on your protocol, and then you run it again. So you're going to have protocol after protocol after protocol after protocol until you get it right. You're going to turn in every single one of those protocols because right here, oh, here's another revision. So you see they went and they revised it. And kept going until they get it right. There's also this box over here for you to put a picture in. So you can take a picture, microscopic picture, and put your picture in here. So when you look back at it, you can say, oh yeah, do you see what it looked like originally where we were all muddy? And then the next one starts to clean it up. And then, when you get to your perfect H&E, you'll have that perfect H&E picture. So you will always have a documented format for that particular hematoxylin that you're using. Does that make sense to everybody?
Yes.
Okay. And it's always scientific process. So you can only make one change at a time. And scientific process says that you can only make one change at a time, because if you make two changes, then you don't know which change actually made the effect. Okay. So and you're gonna do this protocol thing I'm talking about for the rest of the year. And it is not uncommon, especially when we get to special staining and stuff, for one student to have 20 protocols, before they got it right. Okay, so get used to your protocol making. And are there any other questions for me? Okay. Let me stop recording.